In chapter 25 of Young and Friedman, we're introduced to current, resistance, and EMF. This is the beginning of electrodynamics for us, although we'll be dealing with primarily situations of constant current. We'll define the current as the amount of charge passing through some point of your circuit per unit time. The symbol we use for current is a I. Generally, we'll use a capital I if that current is not changing with time, and we'll use a lowercase I if the value of the current is changing with time. So you can think of this as a finite amount of charge passing in a finite amount of time, or as an instantaneous current, an infinitesimal charge in an infinitesimal time, dt. The units of current, therefore, are coulombs charge per seconds time. This is defined as the amp, or ampere, and the unit symbol is a capital A. We follow some conventions which might contradict things that you're familiar with in an engineering circuits course. Current is going to flow from higher to lower voltage. You know already that electric field points from higher to lower voltage. So in that sense, our conventional current flows with the electric field in your circuit. Current represents the direction of flow for positive charge carriers. Unfortunate for us, the historical definition of current is such that the things which are actually moving in the wires, the electrons, which have a negative charge, they are actually flowing against the direction of the conventional current. Current is not a vector. It is a scalar with a defined sense, right? If we have a circuit loop, we'll define whether the current is flowing clockwise or counterclockwise around any given circuit loop. Plus or minus signs will be okay. If you have a minus sign assigned to a current and it's already labeled to be going clockwise, it simply means the current is actually flowing counterclockwise. So we'll have situations where we solve Kirchhoff's rules later where a current might come out to be negative, and that's okay. You don't need to redo your work. You just need to redefine the direction that your current is flowing. Current may split or divide at a node or junction depending on the resistance encountered through each branch. We've defined already nodes and branches in our circuits. Beware again that node means something maybe slightly different than you've seen in an electrical engineering circuits course. Nodes in physics have 3 or more wires at the connection, which allows the current to split. On the microscopic scale, we can look at a wire carrying some amount of current. It has charge carriers, capital N of them, in some length of your wire. The lowercase n we define as the number density of those free charge carriers. So lowercase n is how many there are, capital N, divided by the dV, the volume of the chunk that you're considering. The charge density rho is that lowercase n, the volume density, times the charge of each free carrier. So we're looking at now a chunk of charge, dq, which is equivalent to the number density, lowercase n, the charge of each carrier times the volume dV, and that's simply the number of free charge carriers times the charge of each. The definition of current, dq dt, allows us to write an equivalent expression here where we'll change dV into the cross-sectional area A times the length of that chunk of the wire, dx. Here we introduce something which is defined as the drift velocity or drift speed, which is the magnitude of the velocity vector. The drift speed is simply dx dt. If you follow this chunk of free charges, it's going to drift through the circuit. The current is therefore defined in terms of that drift speed as the number density of free charge carriers times the cross-sectional area of the wire times that drift speed, Vd, times the charge of each. Current density is a vector. We said current was not a vector. Current density is simply the number density times now the Q of each charge carrier. This includes a sign, whereas previously we had only the magnitude, times the vector drift velocity. So you can see here, current density will always be parallel to the electric field in your circuit. And we can define something called the resistivity of the wire or the material through which the current is flowing as the ratio of the electric field magnitude to the current density magnitude. Resistivity now, sorry, it's not charge density. Resistivity rho is units-wise newtons per coulomb, that's E field, divided by amp per meter squared. That's current density. You can show that this is equivalent to, and it's a good exercise for you, show that that is equivalent to an ohm times a meter. Now this is a microscopic property of each material. It has to be measured. And we find that our measurements of resistivity actually depend on the temperature. So the resistivity as a function of temperature, that could be in degrees Celsius or Kelvin, absolute temperature Kelvin, is some reference resistivity, usually taken at room temperature or something similar to room temperature. That's your T0, reference temperature, multiplied by the quantity 1 plus alpha times the quantity temperature minus reference temperature. This alpha is what we call the temperature coefficient. Again, it must be measured for each material that we're interested in. Most materials have an alpha which is greater than 0. Metals fall into this category. What it tells you is that as they heat up, they resist the flow of current more. So it serves as a negative feedback mechanism. If you try to push too much current through a wire, it will heat up. It will become more resistive to the flow of that current. Now, carbon is one of the materials, one of the rare materials that has a negative alpha value, meaning as a carbon filament heats up, its resistance actually goes down, which allows more current to flow, which allows more ohmic heating, and there's a positive feedback loop. And if you've ever burned out a carbon resistor, you've smelled the result of this process at work. If you push a resistor beyond its rated voltage capacity, limit for maximum voltage, you're going to burn it out.